So this scenario of an old finger instead of gold finger, so old man with a bent finger. Uh, James Bond jumps off a cliff to escape a villain. To make it more dramatic, cliff has a ledge, a distance h beneath the top of that cliff, which extends some distance l from the vertical face. Stunt coordinator wants you to determine the minimum speed in terms of the height of that cliff and the length of the ledge that's beneath where that jump is, so that he just misses it. All right? And so to draw it, so we have H, and I'm going to back this up a little bit, and L. So we just have that going for us there. And so James Bond is going to jump off that cliff, okay, and miss it. So I'm going to try to draw a path. There we go. And so there's this path where James Bond just barely misses it. So this is the diagram of the situation that's going on here. And it's a projectile motion problem, but it's not one that requires you using that displacement triangle answer. So I give examples of ones where you do and you don't, okay? And so we can just say, you know what? This h thing, we know it equals half gt squared. We know that the time of flight and the height of a projectile are linked by this equation. And the reason why I can just go straight to that is since it's all x velocity initially and no y velocity, that means it's the same as just if he just stepped off the cliff and fell. His time to make it to the bottom, to the ledge or to where the ledge ends would be the same regardless. So you could do this at home, like you could get, say, 2 quarters on the edge of a table, have one sitting there and fire the other one at it. The first one will just sort of drop off, or will go at a projectile, the other one will just drop, and they'll hit at the same time. You might have to do it a couple times to get it down. And you can watch that happen, all right? So we have that piece of the puzzle, and along the horizontal direction, this is just gonna be that x speed times time. It's just distance equals rate times time, or the first zeroth law. All right, so we have a diagram, we have the variables that were specified, and we use the physics to say this is what these variables could be written as. And the thing we've got to remember, though, is we want a function determine the minimum horizontal speed in terms of L and H. So I want a function that does that. Vx equals something that has the variable L and the variable H in it. All right, that's what we're aiming at. All right, so we have that going for us. So we could take this, let me go back to, so this would mean that T equals L over Vx, which means I could take this thing here and put it into T there. So this means I have 1/2 g times L over Vx squared. So H equals GL squared over 2Vx. So now it's just simple, Vx squared. So Vx squared is just GL squared over 2H, which means Vx would equal, and we just, we take the square root of both sides. That L comes out since it's a squared thing, and you just have G over 2H. So right there, you have a function that answers the question. And so whatever spot we pick, the movie producers pick, we can know how fast James Bond needs to get running, or the stunt person, whatever. And by the way, this is really how it's done. There are people who have this skill and get paid money to answer these kinds of questions for movies. I think one of our problems from Monday was about a court case. And so someone like me could get brought in as an expert witness to do that kind of math and get some really good money. And so if you become a professional engineer, you could make $200, $300, $400 an hour doing the math on some technical problem as an expert witness in some case, where they hire you to come in and give a definitive answer. And you would do something like this, maybe a bit harder than this, but by the time you're a professional engineer, or if you become a scientist, it won't be that hard for you. It'll just be some amount of work that you get paid some seriously good money for. So there you go. We have a function for that. And so it wouldn't matter where we're at if we know H and L. Gravity is a known feature. Depending on what unit system you're in, poof. So whether it's a car, whether it's a whatever. In fact, you could even make a little skid that, they stop the filming right as he runs up to the edge, and then they just put him on a skid and throw him off and resume the film, and they blend that all together. There's lots of ways they can pull that off. So anyways, so that's the problem number one on this. This next one, another movie situation. So summer job working for this special effects team, sequel to the movie Fargo. I never saw that movie, but I heard it was good. A body's discovered in a field. One suspect's a hunter who was seen that morning shooting his rifle in that direction, claims he was shooting at a deer. You're designing a flashback scene which shows his version of firing the rifle and the bullet kicking up dirt where it hit the ground. Sheriff later finds a bullet in the ground, tests the hunter's rifle, and finds the velocity that it shoots. In order to satisfy these folks who demand movies be realistic, directors assigned you to calculate the distance from the hunter that the bullet should hit the ground as a function of the bullet's velocity and the rifle's height above ground. So calculate the distance as a function of muzzle velocity and height above ground. So again, a function where distance equals something in those terms, all right? So the same thing applies before. So if we shoot this bullet, so here's our bullet, okay? It's a really big bullet. We shoot it, immediately it starts dropping, okay? And its time of this height that it drops is still this 1/2 GT square business. So if you could time the device so that the instant the bullet leaves the barrel, another bullet drops from the exact same height, that they will hit the ground at the same time. Laws of physics, okay? And so assuming air drag is probably a little bit of difference due to air drag because of what air drag depends on, but they'll hit at essentially the same time. So again, we have this H equals half GT squared thing about the relationship between the height of the bullet above ground and the time of its flight, period. Anytime something starts at a y velocity of 0 and is under gravity, this applies. And it's the nice thing about this thing. So we could solve this thing for time, and you get the square root of 2h over g. Get used to seeing that equation. And then we know we wanted a function about distance. We know first zeroth law, delta x is going to be Vx times delta t. All right, this is technically a delta t. So now it looks like we probably have this. So speed of the bullet, delta t is the square root of 2h over g, and it looks to me that I have muzzle velocity here, and I have height above ground there. So bam. We made a function that answers the question. And so you might have another way that this sort of stuff shows up in real life is crime scene investigations and traffic accident investigations. So, for example, the traffic accident thing, police forces have a manual, basically, that addresses pretty much every situation that you could encounter in a crash. And if they find one that's novel, then they would have to bring in an expert to finish the deal for them. But they can, based on, tire marks on the ground, distance from where it happened, or they believe it happened, they can figure out the speeds. Because somebody like me or you in your future self as a professional scientist or engineer would have made a formula like this for a given situation, generalizing a problem like this one, etc., or the last one. And so you might make money doing that sort of thing in the future. For the most part, all that stuff is a well-oiled machine. It's not like anybody needs a new version of those manuals, but you're going to get paid to answer questions like this. And this would just be one little piece of a much larger puzzle that involves simulation and testing in simulators and when it gets to it. So the way it works, we do way more simulation than we do physical testing. And we start with simulation because if it breaks, nobody gets hurt, no money lost except the time to pay you. And so when you're talking about hundreds of millions of dollars to billions of dollars of machines, you, like a rocket, or a plane, or you name it, you want to make sure that you've piled all the laws of physics and variables and weird stuff into a simulation. It works. We've bringing forward all the knowledge that came before, and then we go build the thing so that we have a relatively good chance that when we launch it or do whatever, it's not going to blow up or crash on us. And we still do that with rockets. If you've watched SpaceX and all that, they've lost a few rockets because it's a really complicated thing. But they figured it out. All right, but I guarantee you they did a lot more simulation before they got to that phase. And instead of only losing 5 rockets, they would have lost 50 if they just tried it and kept going. All right. Another, speaking of investigations. So this one, a little bit more involved. We're just going to get some answers here. We're not going to just get an equation here. So this thing, a robber investigation, thief robs a bank to escape the guards, went to the roof, threw the money bag to accomplice awaiting at a roof that I believe was lower than that one. And the defense attorney contends that in order to reach the roof of Days, the defendant would have had to throw the money bag with a minimum horizontal velocity of 10 meters per second, but in a test, she could throw the money bag no more than 5. So how are you going to figure this out? All right, so it's a cute problem, but people, like I said, really do this kind of math to really solve crimes and court cases and stuff like that. So we have all this other information. So I'm just going to kind of take a textbook equation-oriented approach here. So the initial speed in the y direction of throwing something horizontally is 0. So I'm just going to write it. For something that is in free fall, okay, 9.8 meters per second every second, which next week, that 9.8 instead of being meters per second squared would be newtons per kilogram. Same thing, units work out. So I've kind of captured, this is undeniably true about this situation, and we've gone over that a few times. What is the change in y position? How far does it fall? Well, we're told that the tower is 250 and the other one is 100. So you have a 250 minus 100 equals 150 meters. That's what our delta y is, all right? We also know that delta y equals v naught y delta t, and then we would have, plus 1/2 a y delta t squared, so have this equation. And so if you solve for delta t, you're just going to get, of course, this is 0. So, and again, this is the combined zeroth law. It pretty much, you could always write it for a motion in any direction, delta x, delta y, delta z, and if you just follow the subscripts, you can't avoid it. So rearranging all this, you're just going to get the displacement over half of g, and so in this case it would be 4.9, and so I'm going to skip some of that math, and you get 5.5 seconds for the time of flight. All right. I suppose we could, and that's just h equals 1/2 gt squared. Okay, so if you look at this right here, delta y is the height, a sub y is little g. Okay, so all I did was take a different approach. But you could have looked at this problem and go, oh, I have another height, there's a time of flight, that would be the same as just dropping it as opposed to throwing it horizontally. Okay, so purposely doing it in kind of a textbook, those equations thing, just for the variety of it. But this is literally the same. This right here, this is just h equals 1/2 gt squared. The blue is probably preferred. It's much more simple, and if you just go to it, it says, hopefully, that you understand what the explanation of why it's that way. Okay, so we have an answer from a vertical analysis of that motion. So we do that. So I guess from a modeling perspective, we want to vertical modeling. That's a really lousy scribble there, chicken scratch. And so then now we want to do the horizontal modeling. And this is, I can tell you all day long that these two aspects of motion are independent of one another in a projectile analysis, projectile motion. They are, and you have to analyze them separately. There's not another way to do that. So now we can just say, all right, the initial speed in the x direction, well, we're trying to figure out what it would be given these other parameters, such as what we just figured out. And in the x direction, acceleration we know is 0. Could you say that there's air drag? Yes, you could say that. It's not going to matter for something this small at this lowest speed. It's just not going to be an issue. If we're talking about a plane or a missile, oh yeah, then you don't do that, because that is proportional to speed squared. Okay, and at those speeds, you absolutely have to account for it. Okay, so those are some basically true things. We know that the delta x was 20 meters because it said The mall below is 20 meters wide. So I'm just picking information from there. We just found out that delta t was roughly 5.5 seconds. You'd probably want to hold more than one decimal place in your calculator when you're doing this sort of thing. And if you're doing this in code, you'll have gazillions of decimal places, by 32 or something crazy like that. All right, so then I could do the same thing again, combine zeroth law. This stuff matters, so delta x would be v naught x delta t plus 1/2 ax delta t squared, and of course, that's 0. And so the combined zeroth law just settles down to be the first zeroth law. That's all that is. And so we can just say, all right, 20 was the delta x, v naught x, I don't know, but the time was 5.5 seconds. So that means our initial x speed, based on the physics of this, is just the 20 over the 5.5, which is roughly, 3.6. So that's less than the 5. All right, so somebody makes a decision, so this is evidence presented in court. And the nice thing about these are laws of physics. This isn't open to discussion about it. And because it's one of my pet peeves, I am going to say something about why the laws of physics demand that masks work for stopping or mitigating the transmission of any respiratory virus. In fact, mitigating anything that travels through the air in aerosols or as an aerosol. So aerosols, what are they? Dirt is an aerosol. Smoke is an aerosol. Over 90% of what comes out of your mouth when you're breathing can't be seen with the naked eye because it's less than 1 micrometer, which is a millionth of a meter or 1/1000th of a millimeter. A human hair is 160 to 100 microns. So you can't see it, but those things will hang in the air for at least minutes, usually hours to days, short of coming in contact with a ventilation system or filters or something like that. These things obey the laws of physics. Many of you will take a fluid dynamics course as engineers, and you will learn about the things I briefly mentioned in the fluids chapter. You'll have a whole course on that chapter that will demand you know something about this course and whatnot. A mask has to work. Now, if your mask is made of toilet paper, it won't work as well as a mask that's an N95 level material. An N95 will do at least 95%, usually more like 98. T-shirts will do 30%. Bandanas, 5%. A face shield, nothing. In fact, it makes it worse because fluid dynamics, the stuff comes around to where you're breathing instead of being kept away. So laws of physics, they make demands on the way things happen in reality. So just like this simple motion problem, there's no way that you throw it at 10 meters per second. I guess it would take a bit more to throw something at 10 meters a second, like you'd have to be a baseball player or something like that. So, or if you did throw it at 10 meters a second, where would it land? That sort of thing. So it would probably go over the building if you threw it at 10 meters a second. So there you go. Laws of physics cover a lot of ground. And so on that mass thing, it's a function of they have to work. It's a material and fit determines how well they work. So that was something that got lost in the debate because nobody was listening to engineers and atmospheric chemists and physicists. So we would have had a much better response to the pandemic had that science not been disputed by pseudoscience and politically and other ideologies, motivations. All right. Next problem. You read in a newspaper about some rock from Mars. Friend says they were shot off Mars by the large volcanoes there, which at one point they were active. You're skeptical, so you decide to calculate the magnitude of the velocity. So here's Mars, here's a volcano, something. So you would have your, initial velocity, some angle, etc. That's the idea. Mars, gravitational acceleration is only 40% of that on Earth. So little g for Mars is 0.4 of rg, or 0.4 times 9.8, if we're going to go in meters here. Let's see here. Assume the rock's 45 degrees. So our theta will be 45 degrees. What is the magnitude of the rock's velocity as a function of its distance from the volcano and the height of the volcano? Okay, so again, this is going to be, we're going to make a function to figure this out. And so astronomers would want to know this. And we would use that if we ever got to Mars and collected data, et cetera, et cetera. All right? So let's go at it here. So one thing we could write is that this distance d from the base of the volcano would have to be the initial velocity x times the change in time. You can't escape that. And so again, the time of flight would be a relatively simple thing here. And we want a function of its distance and height of volcano. And we're looking for the rock's velocity. Okay, so we have some options here. Once again, we can write this combined zeroth law. We could expand it out here like we'll do in this case. So more of this here. So I'll do 1/2 minus 1/2 little g on Mars, g sub m, delta t squared. So we have this function. And so what we could do is take this time factor here and put it into there. All right, and so now we would have y equals y naught plus v naught y, and we would put in this d over v naught x minus g over m over 2, g sub m over 2, and then this d over v naught x, that whole thing squared. All right? So I'll do some ciphering here, so just to make some things explicit, hopefully things that you g sub m over 2v naught x squared d squared. And so did that mainly just to highlight the fact that this right here is going to shake out as a tangent. And the reason for that is you have v naught, oops, change colors. V naught y is v naught sine theta. V naught x is v naught cosine theta. And that's just tangent theta because the v naughts cancel. All right? And if you remember reading in my book, and I'm going to do something else here. I'm going to bring that y naught over. That just is our h. And then we have a d tangent theta minus a d squared times times GM over V naught. I'm going to V naught squared cosine squared theta. This equation is basically if you remember from either textbook, it's basically y as a function of x, except we made it in distance from the thing here. And so this equation here, and since I'm sort of running out of room, I won't do every step, but you get V naught equals the distance times the square root of a big ugly mess. And the nice thing about it, it's the gravitational factor for Mars over 2 cosine squared theta, and then h plus d tan theta. You can see math like this in my chapter 4 of my book. I spend a lot of time going around the block with these projectile motion equations. In fact, I bet you'll find some of that derivation useful past CAC. So that's the function. It gives us the initial speed of the projectile in terms of distance from the, I left the parenthesis off there, from the base of the volcano. And it has, so we have distance and h. So we wanted velocity as a function of how high the volcano is and how far from it. Done. So the problems on the test are no harder than the ones here. In fact, they're not this hard. They're totally not this hard. Now, number 5. These last few get a little bit simpler. Well, number 6 and 7 are a little longer, but all right. World Series, so baseball. So we go from Mars to baseball. So there's somebody trying to steal second. Catcher observes that's happening, gets the ball from a pitcher, throws as hard as he can. If the catcher throws the ball at an angle of 30 degrees on horizontal, so it's caught at the same height as the catcher threw it, so that means no delta H in the range thing. How much time does it take for the ball to travel? 120 feet. All right, so this is where we get to use that thing that I'm so proud of in the in my textbook that nobody else uses anywhere. So 30 degrees. This is 120 feet. So we know that we're dealing with, remember that when we're in feet, G is 32.2 feet per second. And so this vertical leg, half GT squared, will be 16.1 T squared, so half of 32.2. Lift the 1 out there. There we go. That's a really lousy 16.1 T squared. 16.1 T squared. All right. And we don't know the speed, and we'll use T instead of delta T just so it's easier. So the nice thing here is if I look at this leg and this leg, that's a tangent relationship. So tangent of 30 has to equal 16.1 T squared over 120. That's a nice thing because that means T is just going to be the square root of 120 tan 30 over 16.1. And so T would approximately be well, I didn't finish it. compute that. I don't think we need to go over how you can plug that into a calculator. I could have kept it in, say, just a formula mode, if you will, all right? And if I had theta vt half gt squared, and this is range, then tangent of theta would be half gt squared over r, which is gt squared over 2r, which means t is going to be the square root of 2r tan theta over g. Yes. All works out the same. And so that general formula be generally true. In fact, I suspect that a baseball team could actually just use that when they're analyzing their game, looking at the videos and whatever. And a bunch of physics goes into that as well. So not as much as rockets and whatnot, but it's there. All right. Mars. A lot of Mars stuff. This one's a kind of a complicated problem. And basically all of this up here, from here to like here, this is all just stuff that is not critical. This thing will be part of the final answer, but that's like flyover country. It's just telling you about how it gets here. So the biology team designed a probe 2 meters from that. They tell you it can't be more than 11. All right, so what we want to do is for the probe to function properly must impact with a surface velocity of 8 meters per second at an angle of 30 from the vertical. It has to do that, all right? So we could just sort of, step one, modeling, we could bring out our trusty thing here, VT, the range, which we know is 10, and then half GT squared, or G Mars squared. So this idea in our head, but the thing that actually I'm gonna erase this and draw it bigger because I need to point out something it's in my book, and but right here we have, this is accounting for a height above ground that it's launched. So you can't really do that on the over here so well, but this thing is going to it's going to launch, but it's going to land 2 meters lower than where it started. And so since the half GT squared vector arrow is a downward pointing arrow, okay, it's going to make it more negative. Okay, so I'm adding more negative to it, if you will. So I'm plus 2ing it in that regard. And so that, as you saw in the textbook, hopefully, makes things a little bit more involved. So that's just kind of setting up the problem. And if you look at other textbook ways of handling this issue, it gets way more complicated than the displacement triangle. That's why I champion the displacement triangle. We did something like this the other day where we had, an impact analysis thing, a constraint, the ending of the interaction was critical to understanding what its beginning was like. And so this speed, and it's 30 degrees from the vertical again, so we did something like this the other day, and that means that, you know, I have a Vx that's this way, and a Vy that's this way, and of course that's a sine, oops, it's a V sine theta, and that's a V cosine theta, and it's V because it's final V, all right? And so that's some features of this problem, and we have our range over here that we know equals 10 meters. We have our general model, went straight to kind of the bottom line, what does it have to do? So this is a total science engineering problem. What does this thing have to do? It needs to impact at 8 meters per second at an angle of 30. Okay? Whether that's why they really need to do it or not, I don't know. It's just, we can make it anything. We could have it at angle 90 if we wanted. Straight up and down somehow. Which you would get close to 90 with that sort of thing. All right, so we have those things. So we could update our model. So I wanted to be explicit about the model mainly because this little feature of it changes the overall analysis. So I could redraw it and put some more things that I don't know the launch angle. So, because it's going to launch from high up and then hit at another angle. So they're not the same angle. They can't be the same angle. Unless there's something very weird about Mars, which is not likely to be true. It's not like they have different physics. Assuming somebody's there. And I could actually put a number onto this vertical leg because if we use 1/2 gt squared plus 2, right? So this up here, this is basically just going to give us, if you plug and chug all that stuff, 14.25. So I have a number here. So now my model is getting really useful. Worst thing that could be wrong with this model now is it should be -2 instead of plus. Okay, we're going to go with plus. And so we have that. Now we could go for the launch angle. We have enough information to get the launch angle. And so tangent of theta will be 14.25 over 10, and that implies theta is 55 degrees, roughly. Just going to keep it a little bit less, but we have a launch angle. Easy peasy. That's not particularly difficult. Then we could have a launch speed analysis, and that's just going to be the cosine of theta will be 10 over 2.5 v naught, which implies v naught, if you just rearrange all that, you get 6.7 meters per second. And then the final thing, we could check it, all right? Just put, bring it up here. Check the model. So if I put 6.7 t in here, and the I'll use that angle in 10, so we can just kind of keep it simple here with cosine, don't have to bother with. You know, so our cosine will be 10 over the 6 point, oh, it's not 6.7, it's 6.96. It's almost 7, really. And then the t, we'll just leave it there. So that means, or we can, if we solve for t and just put, I'm running out of room, so I'm going to put all that numbers in there. We get 2.5 seconds, which is, oh, I forgot to show that up here on the impact analysis, but if you finish this here, Vx is just going to be 10 over t, and you get, or that equals 8 sine 30, which I think sine of 30 is half. So you get, we're going for t here, not b. Then you get a 2.5 seconds, 2.49. So it checks. And you want to make sure that it checks by putting stuff back into it as much as you can. So that's a lot of scribbling, but every step was technically trivial mathematics. But there's a thought process that associates with doing that, and this is the thought process that you have your undergraduate experience to develop and get to you're not likely to become an expert in only 4 years of regular reflective practice. That essentially never happens. But that's a big chunk of the 10-year run that the development of expertise takes. And I think I talked about that at the beginning of the semester. It takes 10 or more years of regular reflective practice on something to become an expert at it. But halfway through that 10 years, whatever you're doing, physics, chemistry, engineering, etc., you're going to be halfway down that road. You're going to be a pretty knowledgeable person by the end of your undergraduate degrees in this STEM area that you have committed to. People will need to respect your authority, so to speak. All right, last problem here. Hopefully we'll be able to get done early. So this is a car jumping a drawbridge. All right, so we have this situation where there's this gap, okay, to do things. And so initially this car's at the bottom of the ramp and it's going to accelerate up the ramp, okay? And so this is we could call that length, a D1 length, and same angle over here. All right, the second half doesn't matter as much. And so there's this, by the time the driver gets up to the top of this ramp, there's going to be some speed associated with that, and there's going to be a distance, d, or a range, if you will. And this one wants a function, where does it specify that? Determine the necessary constant acceleration of that time gap between the two sides, angle aside, and the mass of the car, which we won't have the mass of the car in this one, so I'm going to leave that one out since we're dealing the kinematics instead of the dynamics part at this stage. So we have our diagram that's got all the information on it. And so there's this relationship between this gap distance, and we want a function for that gap distance d in terms of the length of the first ramp and the acceleration, okay? And we can put the angle in there too. So that's our goal. So there's a time to cover gap thing that we would like to know. And so we have this, bring our model again, t. Well, actually, this will be vt the way that we've done it. FGT squared, we're on Earth, so it's just a little g again. And cosine of theta gives us a nice simple thing here where we can easily have a function for time. And again, this is just something you see it several times in the book, my book. Don't see it that often in other books because they take a harder approach to the mathematics of it. And I'm not a fan of doing things the hard way unless you absolutely have to do that. So there's one thing. And I don't know how to convey, go for something. Go for the throat. Go for the easy kill. What's the easy kill? In a situation like this, cosine is just a crazy easy kill. Bam, I have time as a function of the distance, the gap distance, and the speed. We're on the path here, all right? So that's one thing. I can know the time to cover the gap, and it's trivial, all right? Because we're talking about the gap as the range. It's launching at that level, and it lands at that level. Simple, classic range equation kind of stuff. All right, so now we want to look at the acceleration along D1, this right here, acceleration along D1. This time to cover gap was what we just did up there, all right? So, zeroth law theorem says that one of the versions is going to be kind of this expanded form. I use it as ADS equals V bar dV, which it expands out to this. And so every textbook, including mine, will show this equation. I've never seen one show the simpler version that I'm selling, so to speak. Hopefully I don't run out of room here. All right, and so initial velocity was 0, so this is nice. And so this means that our v squared is just going to be 2a d1, which means v would be the root of 2a d1. So we have two expressions. We know the time, and now we know the speed, and we're looking for d as a function of acceleration and time, okay? And we have v as a function of acceleration, and we have time there. We wanted d1 in there, I think, but I won't bother writing that. Well, distance, just as speed times time, distance rate times time, or the first zeroth law again. This is literally the first zeroth law, just kind of in a little bit of a college algebra-ish disguise, so to speak. And so now you just have d will equal root 2a d1, and then the time will be that's weird. So this right here, v cosine theta t. So I need to got my own stuff out of order, so to speak. Here. Sorry about that. So now I can just put v into there, and so you get d equals 2a d1, and then you would just put in the cosine theta times t. So we have that function now, and that's d as a function of acceleration and time. And it also includes the length there. So that would be a really handy thing to know for a stunt like this, which guess what? How many movies does a stunt like this happen in? Lots. I've seen this in several movies over the years. And so guess what? Hollywood stunt coordinators and whatnot have at their disposal. They have an equation like this, just like they were a cop investigating an accident scene. They've got a workbook that says, when you have this situation, here's the math. Measure this, measure that, poof. Now you need to know, the stunt driver needs to know what speed they need to get up to by the time they leave that ramp so that they don't die crashing that car in some place that it doesn't need to go. All right? So those are 7 problems that are more involved than the first set that we dealt with.